we have another group of cells called intercalated. And we have the type A's and the B's. So two types of intercalated cells, A's and B's. We're going to introduce to you what these intercalated cells do, along with where we have the principal cells. The big idea is that these guys respond to hormones, which means they allow me to alter my sodium reabsorption and my water reabsorption. These guys, and here's the best way to remember this, are for acids and bases. So A for acids and B for bases, if you like. This will be a pH system. This is a water system. All right, so with those, here we have a diagram, and first always get your bearings, like where am I? And I realize it says the lumen of the proximal convoluted tubule in my nephron. That's what this one's for, right? This is for later on. So here comes the fluid, all right, from my glomerulus, that capillary, through the GFR of 125 milliliters a minute. Tubular fluid is coming in, and we know that the glomerulus is a fenestrated capillary. I know big things can't get through it, which way I don't have blood cells in there, red and white, so I don't have large proteins in there. But bicarbonates can pretty easily pass through into the filtrate fluid, but hydrogens, protons cannot, because they're usually bound to amino acids. So we automatically have this pH separation right off the bat. The bases, bicarbonates, can go into my tubular fluid, making it really alkaline. But the hydrogens couldn't go in there. They ended up staying in my peritubular capillaries, and that makes my blood become acidic. I got to fix this. So I need to reabsorb as much bicarbonate as possible. Now this is where the idea gets confusing. We are not actually going to reabsorb a damn thing in terms of bicarbonates. We're going to make new bicarbonate and put it into the peritubular capillaries. And we can see that over here. All right, you see that your little favorite equation? Let's do this just because the diagram's a bit on the faint side. All right, there's your favorite equation right up there. Here's the bicarbonate, and I'll have my CO2 inside of my cell. Here's the bicarbonate flowing through. That bicarbonate, this is sort of the same idea as the central chemoreceptors and the hydrogen ions. All right, go back to the medulla for a second, the cerebrospinal fluid, and the central chemoreceptor called a hydrogen ion sensor. Remember how the hydrogen ion that it's sensing wasn't the one in the blood, but it came from the CO2 plus H2O equation in the cerebrospinal fluid? You guys remember that? That's the same thing here, all right? The bicarbonate that I'm putting in here isn't that bicarbonate. So when I have CO2 inside of my cells, of my proximal convoluted tubule, and since cytoplasm is lots of water, that CO2 plus water creates more carbonic acid, and from there it dissociates into bicarbonate and hydrogens. That's where the bicarbonate comes from, that goes into the blood to nullify that extra hydrogen. And this is where you really want to know the enzyme that really drives this, carbonic anhydrase. Running out of room, otherwise known as Ca. And that carbonic anhydrase really allows the cell to take in CO2, create it into water, and then carbonic anhydrase also allows us to break apart the bicarbonate, boy, my brain's not working today, my carbonic acid into the bicarbonate and the hydrogens. So what they're really showing you here is this. See that bicarbonate right there? That's this one. And when that bicarbonate joins to the acid, the proton that came from this equation, it turned this into that, which turns into CO2 and water. And this could simply just move through the filtrate, or that CO2 could diffuse into here. Is there any other source of CO2 that we could get? Well, what's in here?
Oodles of CO2, 40%,
Right.
40 millimeters of CO2.
Oh, maybe, yeah. There's some amount of CO2 in there, right?
Well, it's an artery.
No, it's actually a capillary by now, in that sense.
Well,
Right? But I could get CO2 from here, right, to come into here. So all you gotta think about is if I have CO2 in the cell, it does that equation, that creates a bicarbonate that is actually used to nullify the amount of hydrogen that was not filtered through the glomerulus but ended up inside of my peritubular capillaries. So about 80 to 90% of our bicarbonates that came in here, right, get converted into other stuff and, in a sense, quote, reabsorbed, right, and put back into the peritubular capillaries. It's just a really bad word to say that it's reabsorbed, because when I first thought about this, I'm thinking this literally goes into there, but it doesn't, right? We just simply replace it with this.
Would it be better to say 80 to 90% is neutralized?
No, because everybody talks about 89% of reabsorption of bicarbonate, so we gotta get just used to the awkward state. You can think about it as 89% of the pH problem is fixed, but most books talk about it as 80 to 90% of bicarbonate is reabsorbed in the proximal convoluted tubule. What you need to realize is that's a really nasty way of saying it, because there actually is no reabsorption. You simply just make new bicarbonates and shove it into the proximal convoluted tubule's peritubular capillary. By the time the fluid then has moved through, when you get into the distal convoluted tubule, you're only down to about maybe 10% of this. Now, and I can do that here as well. All right, this is the remaining part. Now this is the type A, right? That are these guys right here. Now if I want to make my filtrate acidic, or I want to neutralize acidic blood, what you're looking at is the idea known as acidosis, where now the blood has become more acidic. And I want to neutralize that decreased pH. The way to do it is to keep in mind that what you have is hydrogen ions in excess in your capillaries. And then realize you've got a crap load of CO2 inside of the capillary. And when that CO2, watch what happens to it, so you might dream about this. Oh, look how cool that is. Right? It just diffuses right into the cell. The cell's full of water. You do your favorite equation, right? And I create carbonic acid with my carbonic anhydrase enzyme, right? That CO2 plus water turns into carbonic acid. I start making the bicarbonates that are necessary to neutralize that acid condition. And what do I do with the other half of my compound? I dump those hydrogens into my filtrate, which will make my urine slightly more acidic. But I'm trying to fix that excess pH problem or decreased pH problem in my blood. Now, once you get used to the idea of CO2, it doesn't matter where the CO2 comes from, but a lot of it will come from the capillaries. But even the CO2 in here could do this. That the cell will take CO2, create carbonic acid, that dissociates into bicarbonates, and those will go into the blood to reduce the amount of free-floating protons to raise your pH, and the other half of that compound will be dumped into the filtrate. This is what type A intercalated cells will do. Now what if instead of being acidosis, we have alkalosis? Here's the really simple thing. Once you guys write down the word alkalosis, which is an increase in pH, type B cells will handle that problem. Type B cells will handle alkalosis. And what do? The complete opposite of what type A's do. They literally do just the opposite. They're going to dump bicarbonates into the filtrate, and they're going to dump protons into the blood. It's that simple. They just do the complete opposite of type A's. Or you can say A's are doing the opposite of B's, whichever way you want to think of it.
Does this happen based on diet?
whenever your blood becomes acidic and alkaline, it could be diabetics, could be having respiratory issues. Anytime your blood becomes acidic or alkaline, we can do this, whatever the cause is. Okay, so you got principal cells, right, that respond to hormones. You've got intercalated cells, type A's and type B's. The A's respond to, if you want, an acidic blood system, right, and the B's when the blood is too basic. The A's will put bicarbonates into the blood, and the B's will put, B's will put protons into the blood.
Okay, maybe silly, but is tubule cell another name for principal cell, or I'm just...
So when these are interspersed in between normal, everyday, boring cuboidal cells.
Okay.
So if I were to look at this thing here being my collecting duct, actually,
Oh yeah, you have some of those, huh?
it might be in the anatomy notes.
It is.
Well, we have
Shows
one
it.
in here. There we go.
Every
Right.
now and then you have one with
So
microvilli.
those are your intercalated A's and B's, right? And these could be your principal cells, the ones that have the yellow borders. And they're interspersed between the collecting duct cells. You'll have normal cells, you'll have intercalated cells, you have principal cells. And they start here at the collecting tubule and go down the duct and such.
But the tubule cells on the chart were the PCT tubule cells. I mean,
Well, on this side of the
left
diagram,
half of
yes.
the chart
Yeah.
was PCT
You don't,
anyway.
you only have those here.
In the DCT, in the collecting and tubules and ducts, right?
Tubules and ducts in the latter part of the distal convoluted tubule, yes. All right, is everybody okay with this? Okay, just remember the B's do the opposite of the A's. Learn one and literally just flip where the bicarbonates and hydrogen go. In the B's, the bicarbonates go here and the hydrogens go there. Just flip this upside down. All right, the next little part is diuretics and how diuretics affect us. So let's do some drawing. All right. Let's see if we can get this somewhat. Whoa, it's got a kinky tubule. Do that. Sounds like a kneecap. And come over here. We're gonna come up and go up like this. Here, we're gonna go up like this, make it exaggerated so it's easier for us to see. All right, so that's a little better. All right, you have the PCT here, right? You have the loop. And in here, when we look at the amount of sodium that's coming into our proximal convoluted tubule due to filtration, all of this sodium comes in. And we're looking at how much sodium gets reabsorbed in the proximal convoluted tubule. How much of this sodium that got filtered is going to go into my peritubular capillaries. And of that amount, if you look at the amount of sodium in here, you're looking at about 65 to 70% of all the sodium that got filtered in gets reabsorbed right here. And who wants to follow sodium? Water. That means about 65 to 70% of your water will also follow your sodium. Now over here, if I have my gorgeous thick descending and my thin descending and my relatively thin ascending and my thick ascending, there's a nickname for the thick ascending, and it's called the TAL. T-A-L. The thick ascending limb. That's this thing right there. We know that it has a transport mechanism, right, where I can take sodium, 2 chlorides, and the potassium, and I can move the sodium, the chlorides, and my potassium into the tissues, which eventually ends up inside my peritubular capillaries. 25% of our sodium, 25% of this initial amount gets reabsorbed in the tau segment. And I'm close to 95% if I push this to the maximum. Over here, you're going to have the distal convoluted, yeah, I made it too damn big, distal convoluted tubule. And we're going to have another mechanism over here. That's going to be a sodium chloride transporter. And we're going to get sodium to leave the filtrate and get reabsorbed. And we're dealing with about 5% of this initial sodium amount gets to be reabsorbed in the distal convoluted tubule segment. 25% in the tau, and 65 to 70% in my proximal convoluted tubule. So a quick judge of math lets you realize we don't have much left. We're down to less than 5%. And that's going to happen over here in the collecting duct. We'll just call it a CD, for the collecting duct. And we have a transport system of simply doing sodium and potassium, your pumps. And we're looking at about 1 to 3% of your sodium gets reabsorbed in the in the collecting duct of your renal system. Now, why do we care about knowing what each segment of the nephron can do in terms of the amount of sodium reabsorption? Because specific diuretics target specific parts of our nephron. So we can look at the different types of diuretics that we have. The first one is carbonic anhydrase. So let's just do diuretics. And I'm going to use numbers, and we're going to place those numbers over here, so we use this idea. Number ones happen right here, and only right there. And they are carbonic anhydrase inhibitors. And they target the proximal convoluted tubule, which means we can influence that amount of sodium reabsorption. Number one is not a clinically used diuretic. It's a research toy to see how the nephrons work and how we can screw things up and study transport mechanisms. Number two are called loop diuretics. And I bet you can guess where they work. Right in the loop. I bet you can tell me exactly what part of the loop. The tau. Because the only part that we have, that I'm showing you where we have sodium reabsorption. So we have two kinds of loop diuretics. You have highs and you have lows. Now they both make you pee a lot. But the high ceilings make you pee an awful lot. The lows make you pee a lot, but not as much as the highs. So they both create lots of urine. It's just the highs really make you pee a heck of a lot, and the lows just make you pee a lot. They're expensive and mainly used for emergencies, not so much on a daily basis. Does anybody know an example of a loop diuretic? We're going to show you one over here. Ever heard of formosamides or Lasix? It's going to target that part of our nephron. So here's where the twos work. Whoops, wrong color. Right, the twos will target that part of our world. The threes are going to target up here. And I'm running out of space, but the threes will be called thiazides. they target my distal convoluted tubule. These are very clinically appropriate because 5% is a small number. I can work with that. I can modify it, and I can give you various dosages to play with that amount of sodium. The last part are going to happen over here in the collecting duct. And they're called potassium sparing. So K sparing diuretics. Because they will spare potassium secretion. They will reduce potassium secretion. The rest of these are going to be targeting sodium reabsorption. We're going to walk you through how 2s, 3s, and 4s work. So let's try and take this. Now I'm going to focus on just kind of this part right here. I'm going to put it over here. So let me get this kind of set up a little bit in terms of how we want to show it. Size. Trying to draw big enough for you guys to see, but not too big that I run out of space to put things in. All right, so this would be a peritubular capillary. This will be your tau. This will be your distal convoluted tubule. And we'll let the black line represent cells, I think. All right, so now we're going to go and look at how this thing works. All right, so let's do this so that it stands out with you guys. I'm going to try. Yeah, we'll do it with red. I think we can do that. Okay. So we have this transporter that allows sodium, right? 2 chlorides and a potassium, right, to be taken out of the filtrate and into the tissues. Well, one type of diuretic we mentioned there we go. Formosamides, like Lasix, are going to inhibit chloride's ability to attach to this transport device. And since chlorides can't attach, the whole damn thing stops. Right? Because now I'm sort of like saying, all right, you can't go on there, and I need all 4 of these things to be on there before this thing can actually change its shape. So if I keep any one of those guys from landing on there, that thing's not going to work. So having formosamides and like Lasix bind to where the potassium wants to go, potassium can't attach, which means then really I'm not going to get my sodium reabsorption. Which means we're going to get an increase in the amount of sodium inside the filtrate, because I'm now reabsorbing less of it. That increase in sodium, all right, will lead to an increase in water. Because remember, wherever sodium is, water wants to be. And that increase in water, right, will simply just be transported through our distal convoluted tubule, right, down our collecting duct, and you're going to get an increase in urine production. How about urine volume? And that's how Lasix works. It simply keeps the chlorides from binding to that transporter. And the whole key is really, right, to get water reabsorption is it's regulated by sodium ions. So therefore the whole damn thing won't work. And we're actually focusing on just actually what happens to sodium. I don't care about chlorides. Therefore the concentration of sodium in the filtrate increases because less of it's being reabsorbed. And since there's an increase in sodium, that's going to lead to an increase in water. And that simply just means then I pee that more water out through a larger urine volume. That work for you guys? All right, pretty straightforward, and that's would be pretty much what happens with number 3s as well. Then we'll take a bit of a break. So let me draw this up here. Let me replace or reposition those words. So we're going to get an increase in urine volume. All right, then over here, let's just do this. Come up like this. We'll do it the same way. All right. Whoa. All right, there's my narrowing. There we go. Okay. Distal convoluted tubule. This is the tau, right there. But now we're focusing on, so just so you guys can keep track of these. This is where we have the number 2s. All right, that's these guys over here. Now we're going to do the number 3s over here. And these are just things like thiazides. God, my brain is just not working today. Thiazide, there we go. All right. I know that I have a transport system in my cells that transfer now a sodium and a chloride ion into my peritubular capillaries. And now we're looking at thiazides, and thiazides do the same idea as Lasix. They target the chloride, screw around with it, like a competitive inhibitor almost. But the bottom line is then, I can't get sodiums to go into my peritubular capillary. So, therefore, you're going to get an increase in the amount of sodium that stays in the filtrate at this location. That will lead to what? An increase in water volume if you want. That leads to an increase in urine volume. That part makes sense? Okay, now practice this. I'm going to give you guys about a 10-minute break. Because here's the next scenario. We're not going to directly do these guys just yet. We're now going to talk about this. Does anybody know of someone who's on a diuretic? Okay, so if I were to go to the doctor, actually, we'll make Taz my patient. You have high blood pressure. I'm going to give you a diuretic. So here's your diuretic. All right, we're going to give her a thiazide. Oh, you're going to need this one too. This is a potassium-sparing diuretic. I'm giving you 2. I'm giving the black one because I gave her the blue one. Oh, Jesus is right. Right? Your job as PAs and RNs is to come over here and be the RN going, don't listen to Moffitt. He's full of shit. Take this, rip it up, and tell you, what are some nice natural sources of potassium? Bananas or potatoes, right? Just increase your dietary take of potassium because that's going to cause you to lose more potassium. And we're going to walk through that when you guys come back from your break. All right, make sure you understand how these work, then we'll add to it.